Okay, good morning, ladies and gentlemen. 3.1a derivatives, still day one, continued. If you have your note sheet where we left off yesterday, we're going to finish that up quick. And then we're going to finish up to day two as well. I'm going to try to go as fast as possible, but explain as much as possible. Bottom line, what we did yesterday is we were looking and we found derivatives. Okay, we found out that there's two ways to find a numerical derivative. A numerical derivative is simply finding the slope of a curve at a specific point A. Remember, A is going to be some number. So there's this alternative form that's defined here. F prime of A equals the limit as x approaches A of f of x minus f of A over x minus A. This will only find the slope at a specific point. Another numerical derivative, this is the numerical derivative in which we've used pretty much this year, yesterday and such. It's the f prime of A equals limit now as limit as h approaches 0. Remember, h is at very small distance away from our A value. It's how we got really close. And that was found by taking f of a plus h minus f of a all divided by h. That gave me a numerical derivative. Okay, that's basic, a lot of what we talked about yesterday. And now remember, that is only going to give you the slope at a specific point, x equals a. And remember, a is going to be a number, okay? And then from there, we defined it a little bit more general. And what we did was we found f prime of x, not a, x. This is for all x. And we found that to be the derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. And what that did is that gives us an algebraic derivative. Now what that means is that gives us an expression in terms of x. It gives us a quote-unquote rule to find the slope of your f of x function at any x value. So this outputs us an expression, and that expression is going to have an x in it. So if I want to know the slope at x equals 1, I put a 1 in for x, and it outputs it for me. If I needed it at 3 different values of x, okay, I would have to do one of these two 3 different times, whereas if I found the algebraic derivative down here, I could take that rule and I could plug whatever numbers in to get the slope, okay? So we're going to be using the alternative form a little bit. You need to be able to use both of these. So what I did, this is not in your notes. Let's say we had to find the slope of f of x equals 2x squared minus 5x at a particular x value right there. So how we've done it is we've used this algebraic derivative to this point. And all I'm doing is I want to point this out. I want to show you the work involved in doing it. So that a value, okay, this a value right here, this is my a value. So a is 2 in this case. That's why I put in a 2. And we plug that 2 in, and then we plug the 2 into the function, and we expand. That's how we solve our limits for polynomials. We basically expand everything in the top. We make our cancellations in the top so we can put together all the h's, like terms that are h's together, so we can factor an h out of the numerator to cancel it out, to get rid of our 0 over 0 to find out x equals 3. Now, I'm just going to take a second here. I'm just paralleling this so I don't just dive into it right away today, because we're going to find one more numeric derivative today, and we're going to find it using in the alternative form. And some people like this a little bit better. It seems to be a little cleaner for some individuals. So again, this a, we're going to do it the same thing. We found out this derivative down here was 3. The slope of f of x equals 2x squared minus 5x at x equals 2. The slope was 3. If I use the alternative form of the derivative, that is taking the limit as x approaches a of f of x minus f of a over x minus a. So I go through and I replace all those a's in there, okay? So f prime of a, which is 2. So I need to find f of x. Well, here's my f of x function. It's defined there. And over here, f of a, well, that's actually plugging my 2 into my function up here. So I plugged it in there, and it's over x minus a. So as I'm cruising along, this whole side right in here ends up being negative 2. So my whole numerator is 2x squared minus 5x minus negative 2x, so that's why it's a plus. And any point in time, if I try to evaluate this limit, I'm going to get 0 over 0. And remember, that means work harder, find the limit. So because I got 0 over 0, I got to find that pesky little factor that's the same between the top and the bottom. So I take that numerator and I factor it and I say, oh, there it is. So after I reduce that 0 over 0, this part's gone now in the next level. And I plug my 2 in and I say 2 times 2 is 4 minus 1, and I get the derivative as 3. It just happens to be a little bit cleaner for you and a little bit less work sometimes, but you need to be able to utilize both of them. And yesterday, all our derivatives were with respect to polynomials right here, like quadratics and cubics. Today, we're going to look more at rational functions and square root functions, okay? So what I'm going to do here is we're going to use the alternative form to find the derivative, which is the slope of the curve. It can also be called the slope of the tangent of the function at x equals a. And in this case, we're looking at x equals 3, so 3 is my a, okay? And all we're doing is we're learning how to evaluate these limits with rational functions. So remember, my alternative form is simply f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. Again, this is just change in y's over change in x. You know, function form, these are y values, these are x values. So it's really just a slope formula is all it is, okay? So as we're moving and bruising along here, if a is 3, we want to find f prime of 3. That equals, well, what is f of x? My f of x is right there. It's 1 over 2x minus f of a. Well, I got to take my 3, plug it in here. So that's going to give me 1/6, and that's all over x minus a, okay? My function looks completely different right here now. I have a complex fraction. In order to do a complex fraction, and I'm not gonna, I would sit in here and I would question you guys what we need to do. I'm just gonna tell you, step number 1, after we plug in, we need a common denominator in the top of my complex fraction. So what I'm doing is I'm looking here, the denominator of this one is 2x, the denominator of this is 6. Well, I can see this needs an x over an x. This one's going to need a 3 over a 3. So I can see my common denominator in the top is going to be a 6x. So I'm going to say, well, oh, Kruger, you bonehead, left out a very important piece of the puzzle here. Let me drag that little guy back. I'm so glad I learned how to do that. It's really the limit as x approaches 3. Super important part that even I forget to write sometimes, but we need to make sure it's there. So this is going to be the limit as x approaches 3. Now, the top, I'm going to get 3 over 6x minus x over 6x. That is over x minus 3. Well, what I'm trying to do is I'm trying to get that numerator into one fraction, okay? I want it into one fraction. Well, I have common denominators, so most likely you would have jumped across the step I just did, and you're going to jump right down to the limit as x approaches 3, and we're going to say 3 minus x over 6x over x minus 3. And it's a really ugly looking complex fraction. Like I said, typically you can see your common denominators up here. You can probably see it's 3 minus x over 6x. And you're right past this one. That's okay. I need work, but I don't need every integral step. I'm hoping many of us are beyond some of that stuff right now, but I do need something. So here, remember now, I'm really dividing fractions, and when I have one fraction in the top and one in the bottom, the next thing I'm going to do after I get one fraction in the top and one in the bottom, I'm going to invert and multiply. Okay, what that means is multiply by the reciprocal, as I like to call it. So, and again, if I try to take the limit, if I plugged in a 3 in this step, if I plugged it in this step, if I plugged it in this step, I'm going to be getting 0 over, excuse me, 0 every time. If you don't trust me, go ahead and plug it in. But I'm going to invert and multiply, and I'm going to get the limit as x approaches 3, and that's going to be 3 minus x over 6x times 1 over x minus 3. Because we're getting a 0 over 0, we're trying to find that factor that's the same in the top and the bottom. And as I'm looking here, okay, I'm going to write out another step just because so everybody sees it. I can see this 3 minus x and this x minus 3. They're really close to each other. So what I'm going to do is I'm going to say limit as x approaches 3. And I'm going to pull my old -1 trick. I'm going to pull a -1 out of the numerator. That's going to give me -3 plus x. Okay? Rearrange these. Now that you're seeing that, that is the same as x minus 3, isn't it? After I pull that out, now that's over 6x times 1 over x minus 3. Now I have a common factor. Zing, zing. Those go away. Okay, now I have that common factor. As soon as I do this reducing that I did, this 0 over 0 is gone. So really, it's the limit as x approaches 3, and I really am looking at -1 over 6x, okay? Well, if I apply my limit, don't I get -1 over 18? Well, what does that mean? That means f prime of 3 equals -1/18. The slope of my original function, the slope of this graph at when x equals 3 is -1/18. Okay, so that's all we did. And I just want to show you something in your calculator here. If you grab it, if you don't, hit pause and grab it. We can have our calculator tell us these numerical derivatives at the same time. And it's important you know how to do this as well. So right here, I'm looking at the graph of 1 over 2x. And if I went to my menu, and I went to Analyze Graph, and I went to this cute little dy dx, now that we know that's a derivative, I'm going to hit that, and it asks me here in the corner what position. You can see that dot's moving around on me. But if I can tell it what position, if I actually typed in a 3 and hit enter, it is taking me straight to the position that when x is 3, my slope is -0.5555556. Okay? Do you know what -1 over 18 is? That's what it is when it's rounded off. Okay, so my calculator is going to give me, this is not an ordered pair. Notice it didn't write it that way. This is the slope of that black dot. It's the slope. That black dot is tangent to that blue curve right at that point, and that is the slope at which it is tangent to. Okay, so again, you go Menu, Analyze, and you can go dy dx. Let's say I wanted to know the slope at when x is 4. I can type that in. There it is. And there's another slope. This is when x equals 4. This calculator will give us a lot of stuff. However, we need to know how to algebraically do it because the calculator is not always in your hand. Okay? So I'm already a long ways into this. And the next one we're going to find the algebraic derivative of this exact same function. Then I think we're done with yesterday's note sheet. Now remember, your algebraic derivative is f prime of x equals the limit as h not x, come on, Kruger, as h approaches 0 of f of x plus h minus f of x all divided by h. This is going to give us an algebraic rule that will allow us to plug an x value in and find that fractional slope everywhere it is, okay? So I'm going to say f prime of x equals, well, f of x plus h, that's going to be 1 over 2 times x plus h, okay? And then that's minus f of x, well, that's 1 over 2x. And now that whole thing is over h. Check it out. I got a complex fraction again. What do I need to do, number one? Get a common denominator. Okay, my common denominator in the numerator of my complex fraction. So I'm looking here, I can see the first fraction has a factor of 2 and a second factor of x plus h. The second one has a factor of 2 and a factor of h. So they both have the 2. The first one is missing the x, so I'm going to give this times an x over an x. The second one has the 2 and the x, but this one's missing the x plus h over the x plus h, okay? So I'm going to put that x plus h in there and the x in the top one. Just so you know, as I'm moving along, never ever multiply your denominators, okay? And check it out. Guess what I did again, big fat dummy? I forgot my important part, because without that written in there, this is not an equivalent statement as I'm going down, which makes it wrong. So, limit h approaches 0. I know I got an h there. Hey, can we look here? Can we look and say my common denominator is going to be 2x times x plus h, if that's acceptable with you. What's in the top of this one? Just an x. Then I got minus. Now I got a bunch of stuff over here, so I'm going to give it a hug. And I'm going to put that in there because it's important, because I'm distributing this negative to everybody over here. Now that makes that a negative x minus h when I distribute it. So I want to get to the one fraction. So this is going to give me limit h approaches 0 of, what do I get up there? Well, that's gone, that's gone. I get negative h over, crappy h, 2x times x plus h, and that's over h, okay? So we are to the point to where we need to, got one fraction in the top, one fraction in the bottom. We're going to say limit as h approaches 0 of, I'm going to multiply by the reciprocal. There's my negative h over 2x, x plus h times 1 over h. Okay, no matter where I was here, to sound like a broken record, no matter which step I was at, if I plugged 0 in for h, I'm getting 0 over 0 every time, which tells you to work, 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 work. And you're going to get it. And I can get to this point and I can see my h is reduced. I have just eliminated that 0 over 0. And basically I have the limit as h approaches 0 of, I get negative 1 over 2x, x plus h. Okay, now as h goes to 0, that's nothing, right? And what this is going to give me when I plug it in, this gives me negative 1 over, what's 2 times x? So that would be 2x squared. What does that mean? That means my algebraic derivative, f prime, in terms of any x value I want, my rule is going to be negative 1 over 2x squared. Well, let's check it out. Let's see if that works. What's f prime if I put my 3 in there? Well, that's negative 1 over 3 squared is 9 times 2. Why? Look at that. I get negative 1/18, just like I had. Okay. My next one here, to save time, and what we're going to do is I would like you to hit pause and give this one a whirl. Okay, remember f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. It's a new f of x function. Okay, I'm going to hit pause. I'm going to work it out. I hope you try to work it out, and I'm going to come back with all the work on there, and we're going to move on to the next one. So if you went through and you plugged in, you're going to notice I'm like the parenthesis freak. But if I plug in x plus h in for all my x's, it only goes in for that guy right there. And notice when I plugged it in here, I have 5 over x plus h in parentheses minus 3. Is there really a need for those parentheses in this case right here? And the answer is no. So I'm just going to kind of clean them out of there a second just so you understand that. Which means what I'm looking at actually down there is one collective unit because they're not separated by, they're all separated by addition and subtraction. So that's one factor in the denominator minus f of x, 5 over x minus 3, all over h. Like I said, first and foremost thing is a common denominator. And if I look at my common denominators, boom, boom, there it is. It's x plus h minus 3 times x minus 3. So what does that mean? That means this first fraction needs an x minus 3 over an x minus 3. And this second fraction needs an x plus h minus 3 over an x plus h minus 3. So usually what I'm trying to show you here is I'm trying to compress my work a little bit so I'm not going nuts on it. So my next step, I'm automatically going to write out everything in one fraction. Okay, and when I'm saying everything in one fraction, one big fraction in the top over my common denominator I got there. And in this first top of the first one, I got 5x minus 15, that's these two. And then this second one, I don't like this, so I always take that negative and I'll change it and I'll distribute it to the top so I can see I'm distributing a negative 5 to these, and that's going to give me a minus 5x minus 5h plus 15. So when I come through, I'm getting rid of basically anything that doesn't have an h in it, to be honest with you, but you got to make sure it cancels out. It's really easy to make mistakes here. And then in my next step, I'm going to rewrite it as I have a negative 5h in the top over that common denominator all over an h. Now remember, these are always complex fractions in my rational functions. So what I'm going to do, my next step is going to be invert and multiply. Invert and multiply. So I take the first one, the first fraction, times the reciprocal of the second, and by golly, I can see, boom, boom, there goes my 0 over 0. I'm always hunting to reduce some factor of x to get rid of that 0 over 0. And as I cruise along, what happens, that turns into the limit as h approaches 0 of negative 5 over x plus h minus 3. As I take the limit, that's why I put a 0 in here. Basically, any h in your expression goes to 0. So I really have negative 5 over x minus 3 times x minus 3. Do not do the Wassa-West thing of double distributing that. What you want to do is you want to write it in simplest form and write it as x minus 3 quantity squared. So what did we find out? We found out the algebraic derivative of, what did we have? Of 5 over x minus 3. The derivative of that is going to be negative 5 over x minus 3 squared. Okay, now our next one that we're going to cruise with is we're going to take a little gander here at how do we deal with square root functions. Find df dx. You know what that means? All that is saying is f prime of x equals the limit as h approaches 0. I will be back. Somebody's calling. The interruption, but it's f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. That's my derivative. So what we're going to do is we are going to come through, Oh, okay, I need a little bit of room. So what we're going to do is we're going to say the limit as h approaches 0 of, again, plug x plus h in for x, and what I get is I get the square root of x plus h minus f of x, square root of x over h. Again, I'm going to sound like a broken record. If I try to evaluate my limit by putting a 0 in for my h's, I'm going to get 0 over 0. Okay? That says work harder, find the limit. Okay? Doesn't always work as nice as we think. However, what I'm going to do is I would sit here and I would have you guys question me what to do. What do we do with square root problems? Okay? Multiply by the, if you remember, conjugate. The conjugate. And it's always the conjugate of the numerator. Okay? What we're doing actually when we're finding these limits is we are pushing the square root back into the denominator so we can do it. Okay? Because I can't just cross off these two x's here and here and say, whoa, because that's a square root of x on top, and it doesn't simplify, and I can't do that. So my conjugate, if you remember, is, and I'm multiplying everything by it, it is the same first term, it is the same last term with an opposite sign in the middle. Okay? Same first term, same last term, opposite sign in the middle. And the reason we do that is because when we multiply, we get the limit as h goes to 0. When I take that times that, what do I get? I get x plus h minus, last times last, I get x. Now, why, if I took this one and this one, that's the whole point of the conjugate, those two go away and they get rid of each other over h times square root x plus h plus square root x. Again, do not multiply out your denominator. Leave it factored like that. So what I'm going to do is I'm going to say this comes along. What do I get? Well, this is really, I really don't need my parentheses in this particular case again. So I'm going to get rid of those little rascals here quick. And I can see in the numerator, what happens is I have a minus x and I have a plus. Oh, look at there. There's that pesky little h standing out. And I get the limit as h approaches 0 of h over h times square root x plus h plus square root x. That's why I didn't want to distribute down there, so I can still see that. Okay? So after I do this and I plug in my 0, well, that just means every h is gone. These don't because I reduced those. So what do I end up with? I end up with 1 over the square root x plus the square root x, which gives me, I'm adding, so I have 1 over 2 of them, which is what my derivative in terms of x would be. Okay? This next problem, we're going to find the equation of the tangent line. Okay? Hopefully you're sick of hearing this already, but how do I write the equation of a line? I need a point, and I need the slope. And the point, if I need it at x equals 9, the point comes from the original function. What's f of 9? Well, that's the square root of 9. Well, that gives me 3. So my point is 9 comma 3. So my point comes off the original function. My slope is f prime of 9, which is going to be 1 over 2 times the square root of 9, which is 1 over 2 times 3, which is 1/6, is my slope. So if it's a tangent line, I have my point and I have my slope, okay? So I'm going to write my y equals, I'm going to say y minus y1 equals slope times x minus x1. You can leave it like this. That's typically what I do. But if you need to put it in your calculator for anything, all you got to do is shake and shimmy with the appropriate slope. Is you shake and shimmy that 3 over. Either one's perfectly acceptable. But notice I would have screwed it up if I'd have done that because I wrote a third. Okay. So what we're going to do is I'm going to throw a little harder one on here for you. And I'm going to ask you to give this one a try, and I'm going to write it out and go through it like I did the last one. So again, my f of x plus h says take an x plus h, plug it in just for your x, and you get 2 times x plus h minus 5 minus the square root of 2x minus 5 all over h. Because it's a square root function, we need to look for the conjugate, which is same exact first term, same exact last term, opposite sign in the middle, okay? From there, we multiply. That times that gives you 2 times x plus h minus 5. Notice I did corral this in parentheses this time for a reason, okay? That one times that one gives me in parentheses because one's positive. It's the opposite of that. I get 2x minus 5. So really, the reason I have this up here is because I got to distribute to get 2x plus 2h minus 5, and I got to distribute because there's more than one term there, and that gets me right down to here, 2x plus 2h minus 5 minus x plus 5. Okay, I got a plus 5, I got a minus 5, I got a minus 2x, I got a plus 2x. Check it out. Only terms in the top are h's. Usually I would reduce that h out there. I'm just showing you some steps here so that the h's now reduce, which brings me along to the next step. And as I'm coming through, now I'm going to let the limit of h go to 0 because I just reduced out my 0 over 0. So a 0 goes in for h. Well, what does that equal? 2 over 2 times x minus 5 plus 2 times x minus 5. Which is actually 2 over, and I have 2 of these terms now. That's why it's 2 times the square root of x minus 5. And if you look at that, oh, by golly, those reduce. So my algebraic derivative is 1 over the square root 2x minus 5. So, bottom line, rational functions, what are you doing? You are getting common denominators, and then you invert and multiply once you have one fraction over a fraction. Okay. If I have a square root problem, what do I need to do? I need to multiply by conjugate of top. And what that does, and then I go through, and in the numerator, you should only have values with h's in them so that that h will reduce out. After you finally reduce, you evaluate the limit and simplify. So what I have here are, because I'm going to do 2 more polynomials here. Again, I'm going to hit pause. I'm going to run through it like I just did that previous one. Give it a try. Back again, x plus h. That means you got to plug that in for that x and for that x. So your start out should be right here. X plus h cubed minus 4 times x plus h minus the function. Why do I have that? Because the next thing I would typically expand all my stuff up here, and I'd put it together up there so that I can expand it. Well, this first term expanded is right there. Distribute the 4, and then distribute your negative, so that now I should be able to see my 4x has to have a minus 4. There it is. Those are gone. This negative x cubed better have a positive. There it is. It's gone. The only thing left in the numerator are factors with h's in them. The next step I'm going to do is I'm going to factor an h out of everything so I can come right to here. So when I factor an h out of all the circled items here, I have h times that business so that I can reduce out that 0 over 0. So now I can apply my limit. Anywhere there's an h, that whole term goes away, that whole thing goes away. So I'm just left with 3x squared minus 4. And what does that mean? That means there's my derivative, okay? I'm going to give you one more practice for this one. I'm going to pause this out and I'm going to do this one and run it through and we are done. If you're good, shut her down. Are you ready? Sick of hearing? Here's my definition of the derivative. This means plug an x plus h in for every x minus the original function divided by h. Boom, there we go. Typically underneath here, I know x plus h, that's x squared plus 2x h plus h squared, and when I cube it, I know that's x cubed plus 3x squared h plus 3x h squared plus h cubed, so I can distribute that -2 to everybody, distribute that negative, which gets me to here, and then once I have everything expanded out in the top, I always kind of come down and I dial in on this last thing, because that's the only thing that doesn't have an h in it, and I'm like, okay, where are you? 2x cubed, there you are, so those are gone. I got a minus x squared, there it is, it's gone. And notice, there's an h, there's an h, there's an h, there's an h, there's an h. So what I do in the next step is I factor an h out of each one of those and just pull one h out so that I can go bada bing, bada boom. And what that does, that gets rid of my 0 over 0. So that as I take my limit, when h goes to 0, I know that's gone, I know that's gone, I know that's gone, and I'm just taking the limit, and it's 2x minus 6x squared. And what that means is, boom, there is my algebraic derivative, okay? Hopefully you can pause and go back, rewatch any of those. I'm going to try to make up an extra practice worksheet because you would have had lots of practice on these last year, but you're going to be kind of light on practice this year. You will have to know how to do these on your summative for this section. And then after this, we'll learn our properties, and we won't be doing this limit process much after that. So have a good rest of your day.